I'm Vipra Jambare. I am a PhD student at the Center for Nanoscience and Engineering at the Indian Institute of Science. So this work is done in collaboration with Professor Akshay Nayak and Professor Rudra Pratap. Uh, this is the outline of my presentation. So I'll first discuss on why do we want to do this cantilever based measurements, and what is the approach that we are trying to do is through grating based sensing. I'll present some of the simulation results, the fabrication and the measurement, and I'll finally summarize the following. So, as we know that cantilever is very interesting for sensing applications, primarily because they have very high sensitivity to many external stimuli. So, and in this event of an analyte, when it comes and absorbs on the surface, this cantilever basically has two modes of operation. One is the deflection as the static mode, where an absorbed molecule will cause a change in the surface traces, and what we see at the cantilever is the change in the deflection or the initial position. And the other is the mass loading effect. So the an absorbed molecule will cause some change in the mass, and the frequency will change accordingly. So this two modes of cantilever operation is widely explored for different types of applications, such as single molecule detection, photothermal spectroscopy, biomedical sensing, and lots of different physical parameters such as temperature, humidity, and pressure. So, and talking about all this, what is it's so in order to have a very sensitive application kind of sensor, it becomes very important to accurately measure the displacement or the change in the initial position of the cantilever or the shift in the frequency. So these are some of the conventional methods. So here we can see the electrical based. So typically it employs a piezoresistive or a piezoelectric material that is embedded on the cantilever, and then a change in the position will cause a potential change at the output. And on the other hand, we have this optical technique, which is a laser is focused onto the cantilever, and then the change in because of the deflection, the change in the position is detected using a position sensitive photodetector. But this electrical, although it can be incorporated or embedded into a cantilever, and it is compact, but it suffers from low resolution because of the inherent noises. On the other hand, the optical noise, although it's very sensitive, it has the resolution down to femtometers, but it is high and bulky, so it becomes difficult if you want to use your sensor for portable applications. So, in order to mitigate this, people have tried lots of things. One is using photonic integrated circuits where you have input waveguide and then output waveguide. So the cantilever is the waveguide here. So a light is butt coupled into the input waveguide, and then the vibrations are detected based on how much light is coupled into this cantilever. But so, although it's compact, it is poor in sensitivity because of the coupling mechanism, and it's very sensitive to fabrication errors. So, in this work, what we present is gratings-based sensing. So, it works on the principle of interference, where both the advantage compared to conventional techniques is that it's alignment free, it's compact. So, we have both the cantilever and the integration grating can be um, defined lithographically. So it offers you this, and in principle, we can integrate both the light source and detectors as well. So going to the working principle, we have this input and output gratings which are used to couple in and out light into the chip. Waveguide is used to guide light through the circuit, and this we have the intercation grating to couple out light and sense the vibration. So if we have an unguided light which is guided, when it sees the grating, it scatters light into different direction, and then a change in the gap position will cause a phase change, and when it combines back, what we detected the output is a modulated out light. So this is the 2D FTDT simulation. So as the gap position is changed, what we observe at the output is a modulation in the intensity. So this is the basic principle behind the uh, uh, this device. So we went on doing some simulations where we varied the grading period. So we optimized the grading period that the maximum transmission is achieved at 710 the grading period. And so for a change in 13 nanometer plus minus, here we see that the transmission drops only by 5%. And if we look at the left slope, which is the sensitivity, so yeah, the sensitivity more or less remains the same. So, though we went on with this configuration, so in order to do the dynamic measurements, we went this on this configuration where we have a bottom electrode and we have a cantilever on top. So first we start off the fabrication start off with the SOI wafer where we have a 220 nanometer silicon, which is the wave guiding layer. So we do e-beam and then define the waveguides and the gratings in one step, and followed by an reactive ion etching. So this inset shows the grating interpolation grating. And after defining the waveguide, we define the bottom electrode using UV litho and followed by liftoff. And sacrificial layer as a sacrificial, we use amorphous germanium as a sacrificial layer, and on top of that we deposit the cantilever, which is doped amorphous silicon. So and we do another sorry for this we do another UV litho to define the cantilever, and then followed by wet etch and critical point CPD to release the structure. So this picture shows the optical microscope image where we have the input gratings, output gratings, and the cantilever and the bottom electrode. And this is the SCM image. So we went on doing the dynamic measurements where we excite the cantilever using a sinusoidal signal, where and the laser we use a tunable laser which is coupled into the chip via the optical fibers, and then we take it out using optical fibers and put in the photo detector, which is connected to a lock-in amplifier. So in this shows the schematic of what we have done. So we apply a sinusoidal signal and we change the DC bias so that the force increases and the cantilever is position is changed. On top of that, we modulate. We have a overlap signal or VAC. So as we change the VDC, we could see for a constant VDC VAC, what we see is a change in the amplitude at the output. So with that, we captured one of the signal, and then we confirm with LDVs, and the frequency response is almost in good agreement with the measured data. And we check another device, and in this we were able to measure for the same applied voltage in LDV, and this ratings we were able to measure down to displacement down to 4 picometers. So in conclusion, what we have demonstrated is an on-chip silicon photonics-based grading sensor. We have optimized the grading sensor using simulations using 2D FTDT, and we demonstrate integration of silicon photonics and MEMS technology using standard fabrication processes, and we are able to measure picometer range vibration measurements using a chip grading sensor. So I would like to acknowledge the staffs of NNFC and MNCF for their help during this work, and the Ministry of Electronics and Information Technology and DST for funding this work. Thank you.